Our speaker this evening, Professor Annraoí de Paor, was born in Watford on August the 5th, 1940, and I'll let you do the maths on his age. After graduating with a degree in electrical engineering from NUI UCD in 1961, he obtained a master's from the University of California, Berkeley in 1963. Following a short stint as an engineer at RTE, he became a lecturer at the University of Salford, UK. While there, he did research for his PhD and was conferred in July 1967. He was appointed to a lecturership at UCD, but returned to Salford in October '69 as Professor of Control Engineering. In 1974, he was awarded the degree of Doctor of Science by NUI in recognition of his learned papers. He returned to UCD as Professor of Electrical Engineering in 1978, and he held that position until he retired in 2005. In '86, he founded the Rehabilitation Engineering Laboratory at the National Rehabilitation Hospital and directed it until his retirement. We're delighted to have Annraoí with us this evening to give us an insight into what has been a very distinguished career spanning over 60 years. And so, without further ado, I'd like to hand you over to our speaker for this evening, Professor Annraoí de Paor.
Thank you very much, Francis. Now, here we go. A few of my adventures in engineering. I've done a lot of creative work in engineering, and my career has been, my research career has been guided by several things. One thing is you get an idea and you have a light bulb moment when you think you've cracked it, but then you find you're heading into a brick wall, and then you're tossed and blown by waves. But if you're lucky, you get a blast of lightning to give you the final necessary what's the word, advancement or inspiration. And then, having done that, you come through in triumph, you break through the wall, but there's always somebody there, as I've found out, knock your head off. So now, I've done research in lots of areas, and although they're very diverse, they've all been united by the theory of automatic control. And I'd like to talk first of all about the theory of automatic control itself, taking me back to 1967. And then I'll be applying that to the aerodynamics of wind turbines, taking me back to 1978. And then I've done a lot of research over the years in biomedical engineering. Francis just mentioned that I founded a research lab at the National Rehabilitation Hospital. So biomedical engineering has always been one of my interests. And I'll talk about work I did on developing a theory for autoregulation in the kidney. I'll explain what autoregulation is. And then the Earth's magnetic field. This is something into which I stumbled unexpectedly in 1999. And then, following my retirement, I've kept doing research, mainly in the biomed area, which Dr. Madeleine Lowry, she's now Professor Madeleine Lowry, and one of her PhD students. And I'll be talking about that. And that takes me back all the way to 1969. So here we go. Here we are in Russia now, on a winter's day. And I have up here a slide saying that the multivariable system, the XCT is AX plus BU, where X is a vector, n by 1, is asymptotically stable if and only if the real symmetric solution L of the Lyapunov matrix equation A transpose L plus LA is equal to minus Q is positive definite, corresponding to any selected real symmetric positive definite matrix Q. There's a lot of matrix terms, but the important thing is just to note the equation A transpose L plus LA is equal to minus Q, where that symbol T is transpose. If you interchange the rows and columns of a matrix, you transpose it. And as I mentioned at the bottom there, this equation is of fundamental importance in the analysis and design of automatic control systems. And this equation, as the name would suggest, was introduced by a famous Russian named Alexander Mikhailov Lyapunov. And basically, for most of my career, all the research I did in control theory was inspired by Lyapunov. He published the most incredible thesis in the University of Kharkov in 1892. Poor Lyapunov had a very sad end, though. In 1918, his wife got lung cancer and died. And poor Lyapunov was so brokenhearted the day she died that he put a gun to his head and blew his brains out. My goodness. So anyway, I showed you earlier, if you look down the bottom of the screen, A transpose L plus LA is equal to minus Q, the Lyapunov matrix equation for continuous time systems. Now, there's a similar equation associated with what we call a discrete time system, x k plus 1 equal to AXK plus BUK, where xk is the value of the state variable at a particular instant in time t equal to kt. And if we come across these all nowadays in systems controlled by a computer, and there's a parallel theory for discrete time systems, and the central equation in it is A transpose LA minus L is equal to minus Q, and L must be positive definite, corresponding to any symmetric positive definite matrix Q. Now, Lyapunov himself didn't discover this equation, but it's called the Lyapunov matrix equation for discrete time systems because it's based on his ideas. Now, in the Olympic year 1960, famous control engineers Kalman and Bertram, Rudy Kalman is Hungarian and James Bertram was American, and Kalman was doing his PhD in America, and they published a very seminal paper drawing the attention of Western engineers to Lyapunov's work. And I read this paper when I was doing my master's in Berkeley in the autumn of 1961. And in that paper, they gave solutions to the Lyapunov equation A transpose L plus LA is equal to minus Q, and showed how they could be so useful in the design of control systems. And they did this by transforming A to a Schwartz canonical form, S equal to M A M to minus 1. Schwartz was a Swiss mathematician, but they pointed out that although the Schwartz canonical form was very interesting for continuous time systems, there was no similar canonical form for discrete time systems. And this set me thinking. I hit on an idea. And I said to myself, let A be the system matrix for stable discrete time systems. And I did something very strange. I introduced into the control theory literature a transformation called the matrix bilinear transformation. And I transformed A into B using the first one on the left there. And then I took a similarity transformation of B, converting it to what I discovered in the literature, the Routh canonical form of B. And then I converted back using the matrix bilinear transformation again to the matrix H. And now, would you believe it or not, H is similar to A. H is equal to VA, V to the minus 1. So H is the bilinear transform of the Routh canonical form of the bilinear transform of the Schwarz canonical form, sorry, the bilinear transform of A. And it serves as a canonical form for A. So you can apply it like Kalman and Bertram did to evaluate all sorts of interesting performance measures for discrete time systems. Oh, I was so delighted with that, my goodness. And I finally stumbled on that and worked it out in 1966. And I recognized 4 principal structural properties in my matrix H. One is that Hji is equal to -1 to the power of I plus j of Hij. That means if you look at the matrix, at my matrix H, you can see the white elements are this, above the main diagonal are minus the white elements below the main diagonal. So the black submatrix is symmetric and the white submatrix is skew symmetric, and the two are interleaved. Now, oh, I was delighted with this. I was hallelujah, as I said, I was able to prove it. I also found that all the elements above the main diagonal in my matrix are negative. So, hallelujah, I was able to prove that. But here's where life got difficult. I found that, and it was important for the applications, that the sum of the squares of the elements in any column is less than 1. Oh my goodness, I wasn't able to prove this. And I realized I was stumped, because if I tried to publish my matrix, the referee would shoot me down if I wasn't able to prove everything about it. Now, the 4th significant property of my matrix, which was important for the applications, is given in the top there. The my goodness, if you take the ith column and transpose it to make it into a row and multiply it using the scalar product into the jth column, then they're equal to this strange combination on the right 1 minus HI transpose HJ all to the minus to the half by 1 minus HJ transpose HJ all to the half. And as I say, I hope I've explained that. But unfortunately, I couldn't prove it. Oh my God, I was tearing my hair out and dancing in frustration. And then the most extraordinary event of my life in many ways. I was in thinking mode very strongly, and like René Descartes, who came up with the existence proof, cogito ergo sum, I think therefore I am. He did a lot of his thinking in bed, so I think of him dead as a wasp does about overhead. I think I am that wasp when she reaches the point XYZ. And my former PhD student, Jane Courtney, drew this lovely cartoon for me of the wasp above the jar. Now, here I was, I couldn't put all the bits together. So one day I sat down in despair in my office in Salford and I wrote letters to all the matrix theorists I could think of and addressed them, ready to send them off after lunch. And then, in a state of despair, I went out for my daily run with the University of Salford Cross Country Club. I was a very keen runner in those days and for many, many years after. And I remember that day well. We settled on a very hard run, a 10-mile run, out the road to Bolton and back again. So I was running along in desperate state, being dropped by my friends. And suddenly, at the halfway point, there was a flash of light in my brain. And I often think it must have been what happened to, like what happened to St. Paul on the road to Damascus. So I suddenly accelerated to breakneck speed and caught all my friends and ran away from them. And unfortunately, the arrowhead hasn't come out here, but I realized I had hit the center. And I was able to write what was the greatest paper of my brief professorial days. And I got two lovely letters, this red fella and the blue fella, from world leaders in matrix theory when I published that. They were delighted with it. Now, windmills on the mind. In the 70s, just like now, Ireland was facing an energy crisis. And I began to think, how could I help? And I realized that Ireland and New Zealand are the two most windy countries in the developed world. So I began to think about windmills on the mind. And there are two characteristics, two variables associated with the windmill. There's what's called the tip speed ratio, which is the ratio of the tip speed of the blade, R omega, divided by the wind speed. And then down at the bottom here, we've got what's called the power coefficient. And the power coefficient is a function of the tip speed ratio for any given type of wind turbine. for example, you probably all are aware of the American multi-blade wind turbines. They have a maximum power coefficient of about 0.3 and high speed 2 or 3 blades about 0.45. And there's a very famous vertical axis wind turbine with curved blades called the Darius rotor. And then the male of the Dutch type, the famous one, and the Savonius rotor, which is something you'll see actually any day. If you look at the top of a milk fan, you'll see the thing spinning around. That's the Savonius rotor. So anyway, they all lay under a particular curve, but nobody knew what the equation for that curve was. And there's no known equation for that because of insurmountable difficulties in visualizing the wake. The only thing that was really known about it was that as the tip speed ratio goes to infinity, the power coefficient approached 16/27. I won't derive that for you, 16/27. But it made me think again. And in 1978, when one day I was playing with my children in the back garden of our house here in Mount Marion in Dublin, I suddenly got an inspiration. And I suddenly realized that no matter what shape the wake has, its angular momentum and rotational kinetic energy are as if it were a solid cylinder. And I ran in and sat down to work. And 4 hours later, I came up with this equation for the power coefficient in terms of the tip speed ratio X. And it was parameterized by this thing eta, which is the ratio of the wind speed through the center of the turbine and the wind speed around it. And to relate the maximum of this to eta, one sets the CPD eta equals 0, which I did. And I got this wonderful equation relating eta to the tip speed ratio X. And being a control man, I plotted out the root locus of this equation. The locus of the roots of the equation, of which there are 3, as the ratio of the wind speed, the wind velocity through the center of the turbine over the wind speed. And I found that as X increased from 0 to infinity, the eta went from 1 to a third. Now a third was the magical figure that Betz, a German theorist in 1926, he had shown. The only thing that was known about that curve I showed you earlier was that as X goes to infinity, eta approaches 1/3. And here I had it coming out from my theory. So a bit of further work, and I found I had related the power coefficient of the actuator disc, as it's called, to the tip speed ratio. And this was the mystic equation. Oh, I was so excited. And as you can see, if you look at the denominator of that expression under the square root, as CP approaches 16/27, X goes to infinity, agrees with Betz. So here I was so delighted, I decided that I'd love to write this equation on the cliff above the railway station in my native city of Waterford. But I realized that if I did that, I'd fall off the cliff. The motto of Waterford City is Urbs intacta manet. The city remains intact, which dates from Cromwellian times when Cromwell feigned to capture it. But intact, ADP intactus non manet, if I fall off the cliff. And I published this, and people got back to me saying, is there no way you could invert that equation for us and give us CP as a function of X instead of X as a function of CP? And so I did that using the method of Cardano-Tartaglia for factorization of a cubic. And I won't bother you with it, but it's there on the bottom of the screen. And I gave a public lecture on this in UCD in the beginning of 78, or no, late 78, sorry, December 78. And Technology Ireland, which sadly has gone out of existence now, they made fun of me. In those days, wind power was considered crazy. So they made fun of me, and they put this lovely cartoon on the cover of their March 79 issue, and they called it Tilting at Windmills, comparing me to Don Quixote. Now, the editor of Technology Ireland got onto me after this and said, I hope you were pleased by that, Annraoí. And I pretended I wasn't. I said, no, I'm furious. I said, my daughter Eileen tells me you've made me like an old-fashioned soldier riding one of my students' horses. This is wonderful. When my daughter Eileen was a little girl, for some reason, she thought that the students came into college on horses. Oh my goodness. But anyway, I decided that I would have a revenge on the English-speaking world because my spiritual home is the Waterford Gaeltacht. So I told Tom Collins, the editor of Technology Ireland, that I was very annoyed and he must accept a paper from me on the aerodynamics of wind turbines. And he said, of course, that's fine. And I said, one problem, Tom, it's going to be in Irish. And he said, oh my God, no. But he agreed and he published it. So this is a paper that came out in Technology Ireland, the issue July-August 1980. Chorlik Ur John Chaskni Roar Augustin Villenguya, a new theory for the actuator disc and the windmill. Now, and that was this. This changed the whole literature in wind turbine theory. I wrote a lot of follow-up papers on wind turbine dynamics, always giving that particular paper as the first reference. And of course, as you can imagine, I had a lot of pleading letters small over the world. Please, can you give us a translation? Which I did. Now, in 1974, when I was still at the University of Salford, I had a visit one day from a Liverpool surgeon, and he asked me to design a portable minimum energy perfusion machine to preserve a kidney prior to transplant. And the scientific officer in my section, Ernie Harbrook, and I did so. And I want to tell you about that. Now, the kidney, you've got the blood coming in on the renal artery and going out through the renal vein, and the urine goes out through the urethra. But inside the kidney, in its outer wall, there are little filters called nephrons, and they're all connected in parallel. I think there's about 1 million of them in parallel or something like that. And if you plot the mean blood flow rate versus the perfusion pressure, which is the pressure difference between the renal artery and renal vein, you get a curve which goes up. Mean blood flow rises with perfusion pressure. But the very first day we had our machine on trial in Robert Sell's lab in Liverpool, he showed me this curve, the lower curve, that the mean blood flow rate as a function of perfusion pressure in the kidney has this area, that region where the blood flow is virtually constant. And this is called autoregulation. And it's between 80 millimeters of mercury and 200 millimeters of mercury, which are almost exactly the range of pulsatile pressures in the human body. And Robert Sells, when he showed me, he plotted this curve out from our machine, and he said, this is one of the great mysteries of life. Go away and think on it. So I did for years. I read hundreds of papers on kidneys. And finally, in 1976, I came across an interesting paper by a Turkish fellow working in Germany. He showed that once the kidney went into the autoregulation region and emerged from it, higher perfusion pressures, the signal was noisy and it had a definite spectrum. And I came across this in 1980 when I was back in Dublin. So, as I showed you earlier on, there are about 1 million arterioles, they're little fundamental filters in parallel in the kidney. And I said to myself, if the flow through these were oscillating asynchronously, that is, they're not in tune together, we would observe 1 million times the mean arteriolar flow rate with a small noise superimposed. And this was my lightning, the light went on in my brain. Now, I just have to take you through a bit of blood flow rate dynamics. The blood flow rate through an arteriole, that's the little fundamental filter, is proportional to the perfusion pressure P and the port power of the radius. So if the radius is oscillating with period T, as I had suspected, this means that if the flow rate is held constant during autoregulation, the mean value of aortal force must decrease as the pressure rises. The mean value of aortal force this was a shock to me, because I said to myself, you would expect the maximum radius, as when the arteriole is relaxed, would increase with P. So what I'm asking is that the minimum radius, when contracted, should decrease as P increases. This is perplexing. So by this time, it was 1982, and I drew myself this graph, radius of the arteriole against perfusion pressure. And I said to myself, let's say autoregulation sets in at a certain perfusion pressure. What I'm asking is that instead of going up, as the top graph shows, the radius should go down, because the mean value of R to the fourth must decrease. So, my goodness, I said to myself, this is strange. So, I said, this is telling me that the radius relaxes faster as P rises, that upper arrow there, but it must be contracting faster as P rises. And that was an amazing thing. So we need a mechanism which can sense the rate of relaxation and use it to set the rate of the next contraction. Now, this brought me back to my control theory reading in 1961 when I was in Berkeley. I came across a principle just by chance one day by a German called unidirectional rate sensitivity, which is exactly what I needed. I needed sensitivity so that when the radius was relaxing, the next contraction would bring it back. Must contract faster as P rises. And that was it. Now, I wrote out for myself the equation of motion of the arteriolar radius. And it depends, it has three terms in it. What's called the Laplace force, the force with which the fluid inside presses on the wall, the elastic restoring force, the force with which the wall resists that, and the muscle force, a dynamical function of radius, as I had figured out. And here are my equations. I won't go through this in detail, but basically I showed that the muscle force was proportional to the degree of activation, as I called it, by some function of radius. And that function of the radius, I reasoned out, must be like the top of a parabolic hill. And I put this into my equation of motion that I showed you a minute ago. And lo and behold, what came out but this? This series of curves shows the graph of the radius versus time for various perfusion pressures. And you can see as the perfusion pressure gets greater, the maximum radius increases. You look at the curves above. But if you look, the minimum radius is actually decreasing as P rises. And I had it, my goodness. So the unidirectional rate sensitivity was working correctly. And now, from my equations, I plotted out the mean blood flow rate as a function of perfusion pressure. And I found once I had set the maximum output of the differentiator and the feedback path, the unidirection differentiator, I got perfect autoregulation for K to 10.5. I got imperfect or undercompensation for K equal to 10, which is what you observe actually in most kidneys, and overcompensation for K greater than 10.5. Overcompensation is very rare, but I had got it. My theory showed perfect autoregulation for K equal to 10.5. And I had this worked out in 1983, but with all the other things that were pressing for my time, it took me until 1986 to get it published. And there it was in 1986. Now, May 1998, exhausted from marking exam scripts, I stumbled into a great adventure with Liapunov, going back to Liapunov on the internet. I was exhausted from marking exam scripts one day, and I did some hunting on the internet, and I found this amazing problem from Raymond Hyde, Emeritus Professor of Physics in Oxford. He had three coupled nonlinear differential equations describing what he called a self-excited Faraday disk homopolar dynamo driving a series wound motor. And he asked if anybody could prove the absence of chaos under stated conditions. And he said that this could have geophysical and astrophysical significance. And he said mathematicians in Oxford and London had failed him. So I thought, oh my goodness, I've got to try this. I couldn't let this challenge go by. And I solved it and sent my solution to Raymond. And a few days later, he phoned me in my rehabilitation lab at the hospital and said, this is incredible. He said, you've got to come over to Oxford to give us a lecture on it. But he said, in the meantime, you must write it up and submit it to a particular journal, Nonlinear Processes in Geophysics, which I did. And it was published in double quick time. It was out before the end of the year. And when I went to Oxford, I asked Raymond, what the heck is this all about? And he said, oh, it's actually, I was trying to understand the dynamics of the Earth's magnetic field, which has been a torment to physicists for 400 years. So he said, you go away and think about that. And Raymond had ignited a bomb in my mind. And at 3:28, my wife, Mary, I was had about a flu this particular night, and my wife, Mary, had gone to sleep in another room. And all these things happened. The bell went off, the light bulb came on, there's an explosion in my mind. And here's over here in the top right-hand corner is the owl. And at the bottom left-hand corner is my former physics teacher from school, Brother Eddie Laughlin. And on top there, in the upper left-hand corner, is pulling a rabbit from a hat. And I realized I had pulled a rabbit from a 400-year-old hat. Now, to understand what's going on here, we have to journey to the center of the Earth. And if you go under the skin of the Earth, you've got the mantle, the liquid core, and the solid core. And the liquid core is the most important for my theory. Now, I saw this vision. It was unbelievable. In my mind, I saw a vision of the inside of the Earth, and there were two current systems flowing in it. There was a black current flowing out from the center, hitting the outer part of the inner core, going around and coming down again. And then, unfortunately, this has been lost on my slide, but I have a blue current there, and the blue current is going around the core, the central core. And looking at this, I'll have to go quickly for this now, but you can see there on my diagram, I've got the mantle, and inside the red part is the inner core of the Earth, and between them there's the outer core. And the outer core, I postulated that night that the inner core must be rotating with respect to the mantle. That was the first inspiration I had. And then that causes fluid circulation in the space between the inner core and the outer core. And fluid circulation, if you imagine there is magnetic flux from what Joseph Larmor called insignificant beginnings, what happens? Flux is induced by the circular current, and that gives rise to a dynamo voltage. Engineers don't know this as the BLV law, but you can multiply as integrators where things are changing. And this gives rise to ED, which is the dynamo voltage, which is driving current out from the inner core to the mantle. And this gives rise to two other voltages. EHA generates IA, the current going around, blue current, but EHD extracts energy from the blazing moon to sustain the blue current. And by this time, it was 3:45 a.m. and I had the whole thing sorted in my mind. The blazing moon is rotating relative to the mantle. This generates fluid circulation around the axis of rotation through magnetic flux started by Johnson-Nyquist noise. Dynamo voltage drives current out from the blazing moon, and acting on this Hall voltage, the Hall effect drives current around the axis of rotation, reinforcing the flux, and the Hall effect also draws energy from the blazing moon to sustain both currents. My goodness, this all came to me in that wonderful night. And I woke up, as I say, I woke up and started scribbling in my notebook at 3:20 and 3:45 a.m. and counting. I had all the equations worked out. And I showed the Johnson-Nyquist terminal noise, which initiates the magnetic flux. And then it was 4 a.m. when I had written all those equations out. And whoops-a-daisy, sorry. I said to myself, if omega is changing slowly relative to the dynamics of the two currents, IA and ID, let's hold it constant. This was the 7th big inspiration I had that morning. And if I did that, what I found is the dynamics in the ID-IA plane gave me this pattern. The unexcited state is a stable node, as they call it. The boundary between unexcited and excited states is what we call a saddle point. And here we have on the right, stable focus. And this means that if this stable focus exists, and I discovered the following day that omega must be greater than a certain value for it to exist. And I was so lucky that on that night, I made omega big enough. So this is it. If, as Joseph Larmor suggested, you have an initial current flux from an insignificant value, it'll go around this wonderful spiral pattern on the right-hand side, and it will spiral in towards P2, the stable focus. But it'll take many, many millions of years for this to happen. And by now it was 4:20 a.m. and I had my hour, my wonderful hour from 3:20 to 4:20 a.m. on Friday, the 19th of February, 1999. So even a donkey has his hour. I don't know if you know this little poem by Chesterton the donkey. Fools, for I also had my hour, one far field sour and sweet. There was a shout about my ears and pounds before my feet. That was the donkey bringing Christ into Bethlehem, into Jerusalem. Now, the next morning, as we say in Irish, Lá elegant Buarach, the prayer will have another day. The next morning, I plotted out the dynamics in the IA-ID plane. And the first graph here is what I just showed you, if omega is greater than naught. And what happened if I changed omega to be less than naught? The thing would flip. And this is exactly what's observed. Reversal of omega implies reversal of IA, implies reversal of magnetic flux. And every few million years, this happens in the Earth. The magnetic field reverses. And I suspect this is only one possibility. I suspect that the Hall coefficient might change sign in the extreme temperature and pressure, causing a reversal of both IA and ID, but I don't know. And here we have Joseph Larmor banging on the table, and the current IA as a function of time, if we got over the separatrix that I showed you, it self-excites, as foreseen by Joseph Larmor in 1919. Now, Joseph Larmor was Irish, and he spent many years as a prof in Cambridge, but before going to Cambridge, he was a prof for 5 years in Galway. And I'll take you back to a wet day in Belfast in 1913 when Larmer, who's there in the forefront, he unveiled a statue of Kelvin. So Larmer and Kelvin, two great Irish physicists. Now, I'll have to go quickly here. Parkinson's disease. In my retirement, I've been doing research with several colleagues, in particular, Dr. Madeleine Lowry, and she's now Professor Madeleine Lowry, and later her PhD student, Claire Davidson. I did research with them into Parkinson's. I've given a definition of Parkinson's disease there. Involuntary tremulous motion with lessened muscular power in parts not in action and even when supported, and with a propensity to bend the trunk forward, to pass from walking to a running pace, and the senses and the intellect being uninjured. James Parkinson came up with that in 1817. And here, a great person who's been doing research on Parkinson's disease and giving us an insight into what might be happening is Professor Alain Louis Benabit, Joseph Fourier, University of Grenoble in France. He's almost as old as me, so he's now retired, but he pioneered deep brain stimulation for treatment of Parkinson's disease in 1987. And what he did is shown on this slide here. Basically, if you look at this fella, I have a tube going down on the top of his skull, and inside that there are insulated coiled wires going down to a particular area of the brain, which I'll tell you about in a minute. And from the top, there's a junction box. The wire extends through an insulated connection down inside the ear, down to the chest, where there's what is called a neurostimulator, a pacemaker-like device that contains a battery and circuitry to generate electrical signals that are directed by the leads to the targeted structures deep within the brain. And Professor Benabit had the wonderful idea that somehow, if we could only understand it, deep brain stimulation was working by jamming a feedback loop. Now, here I'm showing you a picture of the areas in the brain that are of significance here. And the substantia nigra pars compacta generates dopamine. And when dopamine, this chemical, is in short supply, pathological oscillations set in the subthalamic nucleus. So this was where I came into it. I said, right, let's model what's going on in the subthalamic nucleus by a feedback path. The deviation from zero of the local field potential is related to the deviation from zero of the total synaptic current in the group, and that in turn is generated from Y, from the deviation from zero of the local field potential. And this 2 over pi arctan y over h. This is a mathematical expression for a sigmoidal arctan function, which I used in the model. And the sigmoidal arctan function, as you can see, is a curve that just goes smoothly from -1 through 0 to +1. And as h decreases from 2 to 1 to 0.5, that curve gets steeper. And the slope at the origin is 2 over pi h. Now, this is where the control engineer in me came in. I realized if I plotted omega as a function of sigma, that they're just coordinates of a complex plane. The characteristic polynomial of that feedback system I just showed you is shown there, PS equals such and such. And applying simple control theory, I can find that oscillation occurs for k over pi bh greater than 1. Now, I won't go through this, but basically, the condition for oscillation requires the GJ omega curve to be equal to 1 over df, where df is the describing function. The describing function is a function that you can represent a nonlinear element by, and it relates the describing function is related to the amplitude of oscillation. And the amplitude of oscillation, I showed here this equation, GJ omega equals 1 over df. If I plot it on a complex plane for GJ omega varying, GJ omega just goes around the circle. And for ym increasing, 1 over df goes along the positive real axis, starting for the value h equal to, pi h over 2. And at the intersection of the circle GJ omega and the other line 1 over df, I find that there's an oscillation. And I found a lovely expression for the amplitude of the oscillation. 2k over bh square root of 1 minus pi bh over k. I'm almost there now. And I simulated the oscillation. And there's the oscillation, almost a sort of sine wave. And my formula showed me 0.1527. And when I put this in, it was exactly the amplitude of oscillation. So there we are. So now we're almost there. That showed how to calculate the amplitude of oscillation in the feedback system. Now I injected a dither to model the deep brain stimulation waveform. And I'll just go on quickly. I'll go over this. I've showed that oscillation is extinguished if you put in the dither signal. And to explain how the oscillation is quenched we need the concept of the equivalent nonlinearity, which took me back. It was developed from a primitive base into a powerful nonlinear system tool by the late Robert Simpson and myself. Bob was my PhD student from 69 to 72 in Salford, and was later a prof himself. And we continued working together, and we published our definitive paper in this area, exploring the equivalent nonlinearity. So I've shown here the equivalent nonlinearity for the arctan function. And basically, it looks very complicated, but its maximum slope, which occurs at the origin, is readily calculated as that middle equation. And the condition for oscillation is pi bh over k less than 1. And working through that, we find the amplitude of deep brain stimulation to give quenching of the oscillation is given by that bottom equation, h into the thing under the square root. And this was tremendous. I sent my results to Professor Benefit, amplitude of stimulation against fractional pulse duration. And I sent him the full curve, and he put experimentally measured points on it. And when he sent it back to me, I was fit to be tied. It was just incredible how his points lay on my theoretical curve. Now, I won't go into this, but Bob and I we developed all the necessary theory to explain this. And we had developed this concept in the bottom line there, y hat, the mean value of y over a dither cycle, versus E, the amplitude of the dither. It's called the equivalent nonlinear. And here we are now. My sun is setting. I've retired long ago. And you might think I've been wiping your eye, like Bugs Bunny is doing to this fellow. But I don't think so. That's the end. And a famous poem comes back to me. Death closes all, but something ere the end. Some work of noble note may yet be done, not on the coming men that strove with gods. Well, I didn't actually strive with gods, but I strove with the unknowns. And there we are. There are Mila Mahagov, day shifts long.